So if you're like many people, you have been asking, what exactly is Avogadro's number? What exactly is a mole? And what are they good for? Let's find out. Well, it all starts with the atomic mass unit. Measuring the masses of individual atoms and molecules in terms of standard mass units is inconvenient, so someone invented the atomic mass unit, known as the AMU for short, or even just U. One atomic mass unit is 1.66 times 10 to the power of negative 24 grams. 1 gram is 6.02 times 10 to the power of 23 atomic mass units. These two numbers are reciprocals, and this number is Avogadro's number. Avogadro's number is nothing more than the conversion ratio for converting between grams and atomic mass units. From now on, I'm just going to use Na as an abbreviation for Avogadro's number, so this is just the same as that. Let's play around with this equation for a minute. Suppose I multiply the right side times 1.0079. Naturally, I have to do the same on the left side. Or what if I multiplied by 15.994? Again, I need to do the same on the other side. Well, I hope these numbers look familiar to you. This is the average mass of naturally occurring hydrogen atoms. And this is the average mass of naturally occurring oxygen atoms. And of course, you can look those up on a periodic table. If you have exactly 6.02 times 10 to the 23rd power hydrogen atoms, that's going to have a mass of 1.0079 grams. And it's a similar story for oxygen. When you have that many atoms, we call it a mole. The word mole is simply a word that represents a number. And there are other number words like that. 1 dozen is 12, 1 score is 20, 1 gross is 144, that's a dozen dozens, and 1 mole is 6.02 times 10 to the power of 23. Now suppose we would like to put together some hydrogen atoms and oxygen atoms to make water molecules. We know that for every 1 oxygen atom, we need 2 hydrogen atoms. If we've got 1 mole of oxygen right here, we're going to need 2 moles of hydrogen right up here. So if I multiply the top line by 2 and then add everything up, we will get... So you can see, if you happen to have 18 grams of water, about 16 grams of that will be oxygen atoms, and the other 2 grams will be hydrogen atoms. To write things a little more succinctly, on the top we had 2 moles of hydrogen atoms and 1 mole of oxygen atoms, and on the bottom we have 1 mole of water molecules. Now when you talk about moles, you need to be careful whether you're talking about atoms or molecules. Here I have 1 mole of water molecules. Here I have 2 moles of hydrogen atoms and 1 mole of oxygen atoms. Now hydrogen is diatomic. 1 molecule of hydrogen has 2 hydrogen atoms. Thus, 1 mole of hydrogen molecules has 2 moles of hydrogen atoms. Here's 2 moles of hydrogen atoms. That's the equivalent of 1 mole of hydrogen molecules. Since oxygen is also diatomic, it's a similar story. 1 mole of oxygen atoms would be a half a mole of oxygen molecules. Now, if you just happen to have 1 or 2 moles of something, then of course the calculations are a snap. But what about when you don't? Well, let's look at an example. Suppose we have 100 grams of hydrogen and we want to combine that with oxygen to make water. Exactly how many grams of oxygen do we need to do that? Here's the reaction. I will do the calculation two ways. The first way, I'll pretend that I never heard of a mole. I'll just use the conversion ratio between AMUs and grams and figure it out. The second way, I'll use moles, and we'll see which way works better. So let's start with, you get 794 grams of oxygen. We start with 100 grams of hydrogen. We multiply by this first term to find out how many atomic mass units we have of hydrogen. Then we multiply by this to find out how many hydrogen atoms we've got. Then we multiply by this to find out how many oxygens we want. Half as many oxygens as hydrogens. Now we know how many oxygens. The next term will tell us how many atomic mass units of oxygen we've got. And then finally that will be how many grams of oxygen that we get. As chemical reactions go, this one is about as simple as they get. And look at this huge mess. And this is what it looks like even after I condensed it slightly by not writing out Avogadro's number. Now notice that here you multiply by Avogadro's number, and then here you divide by Avogadro's number. So those numbers will actually cancel out. But you still have to write them because otherwise the units won't make any sense. Even this way, there are still some subtle issues with the units that I'm not going to bother to resolve. Now considering how involved this looks, the actual calculation is not that bad. We're just going to multiply 100 times 15.9994 and then divide by 1.079 times 2. And frankly, you could have come close to this answer just doing mental math, because this is the same 8-to-1 ratio approximately that we saw before. Now let's try this again with moles. We start out with 100 grams of hydrogen atoms. We multiply by this term to find out how many moles of hydrogen atoms we have. We multiply by this to find the number of moles of oxygen atoms we need. And then we multiply by this to see how many grams of oxygen that is. And you can see the calculation is the same. 100 times 15.9994 divided by 1.079 times 2. So I hope you can see that while moles may be confusing at first, they can certainly help to make calculations easier. Thank you very much for watching. Please like and subscribe. If you're interested in being tutored online by me personally, I am available until further notice. You can find some information on that down below or on the About page for this channel.